I'd like to thank the organizers very much for inviting me to speak at this wonderful meeting. I'll be telling you about the localization-delocalization transition. Localization here really is code for many-body localization, but the transition from the perspective of Fock space, and you'll see what I mean as I go along. The work that I'm going to talk about has been done in collaboration with all of these people, of whom Shomi Ghosh is in the audience, and she's also presenting a poster on a part of this work. So please go and look at the poster for more details. And the, the work that I'll be talking about is described in more detail in these two papers, one which has been published and the other which was uploaded to the archive very recently. Okay, so just to set the stage for what I'm going to be talking about in a many-body context, let me first introduce the same diagnostics and the same concepts in the context of single particle localization. So if we think of non-interacting particles in a perfectly crystalline lattice, then it's essentially, because it's non-interacting particles, it's essentially a one-dimensional problem. And we know that if the lattice is perfectly crystalline, then the single particle eigenstates are block states. And if we look at the wave function of a block state, this is what the probability density is. So a perfect block state on this kind of lattice would have exactly the same weight on all sides. And so one can easily see from this that block states are extended. And one way of quantifying the extendedness of a state is calculating the inverse participation ratio, which is this particular quantity. And in the case of a perfect block state, you can see that the inverse participation ratio goes as L to the minus D, where L is the linear size of the lattice and D is the number of dimensions. Okay, so now assume that the lattice in question is not a perfectly crystalline lattice, that there is disorder, but there are still extended states. And so the question is, how do we describe those? So one very useful way of thinking of those states is to say that the presence of disorder essentially removes weight from a certain fraction of states on the lattice, with the result that it's only a fraction alpha which depends on the disorder strength, which actually contributes any weight to the wave function. And then on sites which are contributing weight to the wave function, the weight has to be something like this. And so if you assume a form like this for the weight at the sites which contribute to the wave function and nothing at the sites which don't, and then go ahead and calculate the inverse participation ratio, you will see that, very simply, it just has this form, which we can write in a slightly more complicated form. And you'll see what the utility of this more complicated form is as I go along. So you can see that the inverse participation ratio is going to be L to the minus D times some function which is the volume of the lattice divided by another volume scale. And this volume scale is really the non-participating volume. It's the volume of those sites which are not contributing any appreciable weight to the wave function. Okay, so then
because probability is conserved, it goes elsewhere, so you don't have to take that.
No, so the fact that it's this, that it has to be this, is because of the fact that this is normalized.
It has gone already elsewhere.
Yeah, right. So I'm assuming that it's only these sites, some sites have zero weight and the other sites have this, and the wave function is normalized over the whole lattice, and so therefore there has to be a factor of alpha by W in the denominator. Okay. So now if you look at localized states, on the other hand, and not delocalized states, and ask what the inverse participation ratio for those would be, so those, if not on anything else, at least on dimensional grounds, the inverse participation ratio is going to be something like this. It's going to be the localization length to the power of minus D, where again D is the number of dimensions in which the lattice exists. And this can also be written in scaling, in this particular scaling form as the scaling form n to the minus D times a function which is the ratio of the linear dimension of the lattice divided by the localization length. And so from these simple arguments, you can see that if you had to write down a form for the inverse participation ratio for delocalized states and localized states, the natural thing to do is that for delocalized states, you have this volumic scaling, L to the minus D, times a scaling function of the volume of the lattice divided by some other volume scale. And on the localized side, it's linear scaling, where the scaling function is a function of the linear size of the lattice divided by the localization length. However, the point is that these are actually not two distinct kinds of scaling, because for a hypercubic lattice, the volume of the lattice is equal to the linear dimension times, the linear size times the number of dimensions of the lattice. And so each of these scaling functions can be cast in the form of the other scaling function. So a volumic scaling function can be written as a linear scaling function, and a linear scaling function can be written as a volumic scaling function. So there really isn't any fundamental difference between the forms of these two in the case of a hypercubic lattice. Now, if we assume that there is a localization-delocalization transition, and at the transition, the inverse participation ratio goes as L to some minus dc to some dimension, then one can actually write down more concrete forms of these scaling functions. So I'm assuming now a volumic scaling function both on the localized side and the delocalized side, and one can in fact argue from this, from the existence of this critical point, that the scaling function has to have this particular form on the two sides. Okay, so the important thing is that on both sides of the transition, you have a volume scale, or equivalently a length scale on both sides of the transition. And in fact, this length scale is the thing which diverges at the transition. And this is something which was numerically calculated many, many years ago, that there are these two length scales, one on the localized side and one on the delocalized side. On the localized side, the length scale is just the localization length. On the delocalized side, it's really the length scale that's associated with this non-participating volume. And both of them, for an Anderson transition in 3 dimensions, diverge as a power law, and you get a critical exponent which actually ends up being the same for both. It also turns out that at the critical point, the wave function has a multifractal character, and that can be seen by looking at higher moments of this inverse participation ratio. But I'm not going to go into that. But it's well known that the wave function at the critical point has this multifractal character. Okay. So having defined these scaling functions and having shown that the inverse participation ratio is a good diagnostic to actually track the localization-delocalization transition, what we are going to ask is whether this idea can be imported to look at a many-body localization-delocalization transition as opposed to a single particle transition. So to set the stage for that, let's just look at what would be the best setting in which to look at the many-body localization-delocalization transition. And it turns out that the most natural setting is actually Fock space and not real space, because we are looking at, so if you think of extremely localized states, extremely localized many-body states, then they're best labeled by the occupancies of the sites on a lattice. And those states naturally form the basis for the Fock space of the system. And so what one can do is one can actually think of those basis states as points on a Fock space graph or a Fock space lattice, and then ask about the form of many-body localized states and also about the nature of the transition in this particular setting. And so, of course, if the many-body localized state has been formed just by populating single particle localized states, then in some sense it's trivially many-body localized. But you can ask, nevertheless, what does that mean for the structure of the wave function of such a many-body state in Fock space? And of course, if it is not trivially many-body localized, meaning that you aren't obtaining it just by populating single particle localized states, then the question becomes even more interesting. What is the structure of these many-body localized states in Fock space? And one can also define a distance in Fock space, and that is just the Hamming distance of the corresponding Fock graph. Or in other words, how many, if you're thinking of your elementary degrees of freedom as being spins, how many spin flips do you need to go from one side on the Fock graph to another side? So that's a natural notion of distance on a Fock graph. Okay, so a little, just a couple of slides about very quickly about what we think we know about many-body localization. So, of course, interactions are natural in many-body systems, and so the question is, what happens when you have the interplay of disorder and interactions, and is there a localized phase? And if there is, that's the many-body localized phase. And as most people attending this meeting would know, that it's probably only in one dimension that this phase truly exists. And so all the discussion and almost all of the work on many-body localization has focused on one dimension. And so the question is this many-body localized phase actually stable to interactions in one dimension, meaning that if you create a many-body localized state by populating single particle localized states and then switch on interactions between the particles, does the many-body localized state survive or does it not? And indeed, there have been arguments which have been put forth for the stability of the many-body localized state in various forms, perturbative arguments, arguments that have to do with local integrals of motion. And in fact, there's also a mathematical proof of the stability of the MBL phase, which we heard about earlier in this meeting from John Imrie. Nevertheless, one knows, of course, that the MBL phase is not indefinitely stable, that you can destabilize the MBL phase and go into an ergodic phase. And so you can ask, what are the mechanisms which destabilize the MBL phase? Assuming that you do have an MBL phase and you then want to make a transition into an ergodic phase, how exactly does that happen? And it turns out that there are two mechanisms which have been identified for systems with disorder. One of which is what you might call Griffith's destabilization, where what you're saying is that just by random chance, you could have some contiguous region in your system which actually looks like a thermal region, a locally thermal region, because the level of disorder is low. And then this region is coupled to the rest of the system. And then this coupling can actually cause it to swallow, if you like, the rest of the system systematically, and eventually cause the entire system to thermalize. And so this particular mechanism is also what's called the avalanche mechanism. And so this is one of the mechanisms that can cause this destabilization. However, it turns out that for this to be the mechanism which destabilizes the MBL phase, you have to be able to nucleate a large enough thermal region. And at least for systems which people have studied using exact diagonalization, there isn't really any evidence that the systems are large enough for this kind of nucleation to happen, for this kind of thermal region to actually exist. Nevertheless, even in those studies, there is something which looks like a transition that's observed between the localized phase and the delocalized phase. So clearly there has to be some other mechanism to destabilize the localized phase. And so that mechanism is, what some people call a Mott destabilization mechanism, because it's very similar, at least in spirit, in terms of physics, to what happens with variable range hopping in the case of a regular Anderson insulator. And the idea is that you have states in Fock space. And so I sort of schematically represented these states in terms of what their local energy is in Fock space. And so you have states in Fock space which are very close in local energy. And those can be coupled by the hopping term in the Hamiltonian. And of course, to what order in perturbation theory in the hopping you actually couple these states to would depend on how far apart they are in Fock space. I mean, what their Hamming distance is to get from one to the other. And so this mode of destabilization says that as you approach the transition from the localized side, what happens is that you have a large number of these states of the same energy, these so-called resonances, which are also not that apart in Fock space, so they can be coupled by terms which are fairly low, which in terms of the order of the perturbation theory are fairly low, and you have a proliferation of such resonances as you approach the transition, and that is what ends up destabilizing the MBL phase. So for the rest of my talk, to the extent that I'm even going to be talking about any mechanism for the MBL transition, it's really going to be this and not that, because I'm going to be talking about studies, exact diagonalization studies on systems, on microscopic systems, and those would really not be, would really not fall in this particular regime for this mechanism to be important. Okay.
Question.
Yeah.
So in case you put such a pocket of thermal region, does it grow? I mean, is there a critical size over which it just grows?
Well, okay. So that really has to. I mean, so that's at the heart of the question of whether the MBL phase is stable or not. So the idea is that you have this thermal region, and you can think of this thermal region as a bath, and basically as something which has random level spacing statistics. And so there's a certain mean level spacing that's associated with this bath. Now the bath is coupled to the rest of the system, and there's a certain coupling strength. And so it really is an interplay between the coupling strength and the mean level spacing of the bath, which determines whether the bath is going to grow or not. Okay, and so so that's how. So as the bath grows, what happens is that the mean level spacing gets smaller and smaller, but then the coupling strength would also change. And so the question is, will the coupling strength change in such a way that the bath would keep growing and eventually swallow up the whole system? That's okay. Anyway, so with that, let me now get to a concrete model that we've been studying, and which most people have actually been studying in the context of many-body localization, which was this model of spinless fermions hopping on a one-dimensional lattice. And so you have a nearest neighbor hopping, you have an on-site potential, which is where the disorder goes in, and then you have a nearest neighbor density-density interaction. And so it's this quantity epsilon I, which is basically a random variable that's chosen from some uniform random distribution of strength W, which is the strength of the disorder. Now the point is that this Hamiltonian that's written in real space can also be written in Fock space. It can be expressed in a Fock space basis. And it turns out that when you do that, the Hamiltonian in this Fock space basis has the form of a tight binding model on this Fock graph. This is also something that my collaborator Shubhalan Banerjee emphasized in his talk from a couple of days ago. And so on this Fock graph, this Hamiltonian looks like something which actually has a hopping term between Fock space sites and also an on-site potential term. And the on-site potential term is the term which contains the effect of the interaction and also the disorder. And so it is random. However, this is not like an Anderson problem on this Fock space graph, because the disorder that you have on the Fock space graph is actually going to be highly correlated for reasons that Shubhalan explained in his talk. So this is not really the Anderson problem on a Fock graph, because the disorder is highly correlated, and it turns out, in fact, that these correlations are key to even having localization in the system. So once again, so the question is, what do these MBL states look like in Fock space? I mean, that's what we're trying to, that's one of the questions that we're trying to answer. And how can we describe the ergodic to MBL transition in this setting? Okay. So right at the beginning of my talk, I told you about the scaling of the inverse participation ratio and how that can be used to locate the transition. And there I told you that on hypercubic lattices, there is really no difference between volumic scaling and linear scaling. However, it turns out that there is a difference when the lattice in question is this Fock graph, because the volume of the Fock graph is really just the Hilbert space dimension, and the Hilbert space dimension doesn't go as the system size, the real space system size to some power, like for a hypercubic lattice. It actually is exponential in the size of the real space lattice. And so because the volume now is exponential in the linear dimension, volumic scaling and linear scaling are no longer the same thing, and one has to make a distinction between them and ask that to the extent that such a scaling even exists in the localized phase and the delocalized phase, which is the appropriate one for which phase? Okay, and so this is the question that has been addressed in the past, and so it's been argued that the right kind of scaling is actually volumic scaling in the ergodic or the thermal phase, and linear scaling in the localized phase, in the localized or the MBL phase, that is the appropriate kind of scaling. And in fact, I'll show you that that is indeed true from the numerical calculations that we've done. This argument has been made not just for the inverse participation ratio, but also for other quantities like the participation entropy. And in fact, even in a single particle setting, it's been argued that this is really the right kind of scaling for the localization transition on a random graph. So for the regular Anderson transition, but on something called a random graph, which also has this feature that the volume of the graph is exponential in the linear size of the graph. Okay, so what is it that we are actually after? What is it that we are calculating? So what we're going to calculate is a Green's function in Fock space, and more specifically, the self-energy that one obtains from this Green's function, because it can be argued that the inverse of the self-energy, the reciprocal of the self-energy obtained from this Green's function, is like the lifetime of a state that's initially localized on this Fock space graph. So if you happen to be in the ergodic phase, or the thermal phase, and you start with a state that's localized at some particular site on this Fock space graph, then over some finite time, over some time scale of order 1, you would expect the state to get completely delocalized. On the other hand, if you happen to be in the localized phase, then you would expect that in the thermodynamic limit, the time scale over which this delocalization happens is infinite. And so therefore, the reciprocal of that time scale, which is the self-energy, can be used as an order parameter for the localization-delocalization transition. This is something which is going to be finite in the thermal phase, and it's going to go to 0 in the localized phase. Okay, and so this is a slide which tells you that similar ideas have also been used in the case of the Anderson transition, that one can talk about a self-energy of the single particle Green's function and use that as an order parameter to look at the regular single particle Anderson localization-delocalization transition. So what we've done is we've calculated this self-energy using a particular technique which allows us to obtain the Green's function quite efficiently through a recursive method. And my collaborator Shubharan Banerjee described this recursive method in his talk, so I won't go into details. The most important feature of this method is that unlike exact diagonalization studies which require a numerical diagonalization of the entire Hamiltonian, here in this method we don't actually ever need to really deal with the full Hamiltonian matrix. We obtain the Green's function slice by slice, starting from the top of the Fock graph going down to the middle, and the slice in the middle is actually the largest slice. And the most computationally expensive thing that we have to do is invert a matrix of the dimension of the middle slice, which is always lower than the total Hilbert space dimension. And this gives us a slight advantage, actually, in some sense, a considerable advantage over exact diagonalization studies, in the sense that we can go to larger system sizes than are typically accessible through ED. Okay, so anyway, so we go ahead and we perform this calculation. And so this is a quantity that we are after. And we can write this as the Hilbert space dimension to the power of -1 minus ds. And ds here is basically the fractal dimension of the particular state that we're looking at. So if we are in the thermal phase, then we expect this object to be of order 1, and so the fractal dimension would be equal to 1. On the other hand, in the localized phase, the fractal dimension is not going to be equal to 1 because we expect this quantity to go to 0 as nf goes to 0. So we're going to have some fractal dimension which is different from 1. And of course, if you had a completely localized state, then the fractal dimension would be equal to 0 because this quantity would go to 0 as the inverse of the Hilbert space dimension. So if you have a ds which is between 0 and 1, then you have a localized state, but not something which is exponentially localized in any sense on this Fock graph, but rather something which is fractal, and hence this is the fractal dimension. Okay, so anyway, so what we do is we obtain this particular quantity numerically, and then we try to fit our volumic and linear scaling forms to the numerical results to try to obtain this volume scale in the thermal phase, which would diverge at the transition, and this length scale in the localized phase, which would also diverge as we approach the transition. And so let me just show you some numerical data quickly. So first of all, the fractal dimension that we obtain as a function of W looks like this, and Subroto had also shown you this plot in his talk. So the fractal dimension is equal to 1 everywhere in the thermal phase, and then at the transition it drops discontinuously to a value that's less than 1 but greater than 0, and then after that monotonically decreases as W increases, as you would expect from what I told you earlier. This is a plot of the self-energy as a function of the Hilbert space dimension, from which we can actually obtain these exponents. But we can also fit this quantity to the scaling forms that I showed you to obtain the volume scale which diverges from the thermal side and the length scale which diverges from the localized side. And so this is a fit to the volumic scaling form on the thermal side. And what we see is we do indeed extract a volume scale, which appears to be diverging at the transition, and in fact diverging in this particular fashion. Now, please note that even though this looks like, this has a Kostelis-Tsalis form, this is very different from the Kostelis-Tsalis scaling that people have been talking about in the context of the MBL transition, because there the quantity which they argue displays this Kostelis-Tsalis scaling is actually a real space localization length which diverges from the localized side. This, on the other hand, is a Fock space volume which is diverging from the delocalized side, and that volume has this particular kind of Kostelis-Tsalis scaling. As far as the length scale which diverges from the localized side is concerned, so we can extract that as well from fitting our data to a linear scaling form. And that, from our analysis, seems to diverge as a power law with a particular exponent, which is also what typically happens when you try to extract this kind of a diverging localization length through exact diagonalization studies. No matter what the method is that's employed, typically what people find is that you actually get a power law divergence with some exponent, and the exponent violates this particular bound that Aarti Garg was talking about in her talk. Okay, so we see this, and as I showed you in the previous slide, we also obtain a fractal dimension for the states on the localized side, which means that those states are not exponentially localized, but actually display some multifractal character on the Fock graph. Okay, so these were our results for the case of for a system in which we have true random disorder, the disorder obtained from a random distribution. But what we've done is we've also done the same calculation for a system in which the on-site disorder is actually not random but deterministic and comes from a quasi-periodic potential, which is this form. Many of you might recognize this model without the interaction term as the Aubry-Andre model, a model of a quasi-periodic system, which actually, even at the single particle level in one dimension, has a localization-delocalization transition. We are looking at the many-body version of that. And so we went ahead and performed a similar mathematical calculation for this model. And once again, we see that there is a volumic scaling of the self-energy on the thermal side, and there is a linear scaling of the self-energy on the localized side, and you have a diverging Fock space volume with a divergence that's quite similar to what we observed for the localized system, for the disordered system. And again, we have a real space localization length which displays a power law divergence at the transition, but with a different exponent compared to the truly random case. Okay, so there doesn't seem to be a qualitative difference on this level between the truly random system and the quasi-periodic system. But we went ahead and we also looked at other quantities that we can calculate from a particular procedure, this procedure of obtaining the Green's function. So the Green's function and the self-energy that I was talking about so far, or at least the Green's function from which the self-energy was obtained, that particular Green's function that I was talking about so far, was basically the diagonal element of the Green's operator on the Fock space graph. But we can also look at off-diagonal elements. And so we look at two different kinds of off-diagonal elements. So one is an off-diagonal element of this Green's function operator between the very first site of the Fock space graph, which corresponds to all the particles being on one side of the real space system with open boundary conditions. So that is site number 1 on the Fock space graph. And so we can look at the off-diagonal element between that site and a site in the middle slice of the Fock space graph, because most of the states lie in this middle slice, and in some sense, a state in the middle slice is most characteristic of the states in this Fock space graph. So that is one kind of off-diagonal matrix element that we've looked at. Another kind of off-diagonal matrix element that we've looked at is a matrix element between different sites in the middle slice. So this is between the most extreme kind matrix element between the most extreme kind of state and the most typical kind of state, and this is between two different very typical kinds of states. And what you can do is you can actually extract length scales, real space length scales from these two off-diagonal Green's function elements. And so I'm not going to go into the exact details of how these length scales are extracted. This quantity GMMR is basically the typical value of the off-diagonal matrix element of the middle slice. And it just turns out that this Fock space distance of the middle slice is something which can be used as a proxy for a distance in real space. And so you can actually think of this R, even though it's a Fock space distance, as like a length scale, as like a distance scale in real space. And so the corresponding length scale that you obtain here is like a real space length scale. And it turns out that unlike the other real space length scale that we obtained, the localization length coming from the localized side, this one does not diverge at the transition. One can, of course, define another length scale which will diverge at the transition, which is basically this length scale, the reciprocal of this length scale minus the reciprocal of its value at the transition. And so that the corresponding length scale is going to diverge at the transition, and it does with an exponent of about 0.9. Now, the reason that these quantities might be important is that if you go back to what I told you right at the beginning of my talk about this destabilization of the MBL phase through resonances, this mod destabilization, mechanisms for that kind of destabilization actually predict that there is a length scale associated with the range of the local integrals of motion on the localized side, which does not diverge at the transition, but this associated quantity does with an exponent that's close to 1, and that's indeed what we obtain, what we see in our numerics. So maybe one can associate this length scale that we get from the off-diagonal matrix elements with the length scale associated with the local integrals of motion, perhaps, just from the fact that it does seem to match the prediction of this theoretical model, and also with an exponent that's very close to what the model predicts. So in the remaining 1 minute that I have, let me just very quickly tell you that in our calculations, we also do see a difference between, so we see all these qualitative and quantitative similarities between the truly random system and the quasi-periodic system. But it turns out that there are also differences that we can observe when we look at the distribution of the self-energy. And so when we look at the distribution of the self-energy, and in fact the fluctuations in this distribution from sample to sample for the random case and the quasi-periodic case, it seems like there are strong fluctuations that we see in the random case, but fluctuations which seem to be disappearing with system size in the quasi-periodic case. And so the fact that we have these strong fluctuations, these strong sample-to-sample fluctuations in the random case, is consistent with what has been observed for other quantities before, and it might have something to do with Griffith's effects, even though Griffith's effects you would expect would not be very prominent or very clearly visible in such finite size studies. Okay, so with that, let me just come to my summary that this Fock space, Fock space does seem to be a very natural setting in which to look at the localization-delocalization transition in the many-body case, or in other words, the ergodic to MBL transition. And one can actually use the self-energy obtained from the Green's function in Fock space as an order parameter for this transition. And there are different scaling laws for it on either sides of the transition. And then there are also there's a diverging Fock space volume, which is associated with the transition on the thermal side. There is a real space length scale, diverging real space length scale from the localized side. And then there's also a non-diverging length scale, which is perhaps related to the scale over which the local integrals of motion decay, which can be obtained from this Fock space Green's function. And we do see some differences between a truly random system and a quasi-periodic system. So thank you very much.
Okay, questions?
So does it matter which basis you use in Fock space? Your conclusions depend on that?
Well, okay, so when I've set Fock space here, and I've drawn this Fock space graph, I've assumed that the lattice points of this Fock space graph are labeled in terms of the occupancies of the individual sites. And the reason that you do that here, the reason that that's the thing to do, is that you know that if there was no hopping in your real space Hamiltonian, if all you had was the interaction term and the on-site disorder term, then those states would be the eigenstates of the Hamiltonian. And so all your states would be completely localized at these lattice sites. And so it's best to define the lattice in this basis, because in this extreme limit, you know that the eigenstates are completely localized states on this lattice, and then when you turn on the hopping, you see superpositions.
As far as the signature of transition is concerned, is it basis independent statement? That's what I want to know.
Well, okay, yeah. So the signature, one completely basis independent signature of the transition is if you look at energy level spacing statistics, right? So you just, which is the most common diagnostic, and that doesn't require any basis.
It'll give you the same power laws?
Well, okay, so you can't extract these quantities from energy level spacing statistics. Energy level spacing statistics, what happens is that on the localized side, the system is supposed to be integrable, and so if you look at the energy level spacing statistics, it's Poissonian. On the thermal side, it's supposed to be completely random, so you see random matrix statistics. And so there are appropriate diagnostics to distinguish between these two limits in the level spacing statistics, but you can't extract these critical exponents.
So these critical exponents are specific to the real space basis. This is what I want to know.
I mean, yes. So, for instance, the localization length that you're talking about is a localization length in real space.
Makes sense. Yeah. Okay. Thank you.
Other questions? There were a couple of questions during the talk. Well, if not, then let's thank all the speakers.